Module 4, Decision Support Systems, DSS in Agriculture. Definition and importance. At the beginning of agricultural history, farmers have relied on their manual forces, intuition, and situation analysis in the decision-making process. Presently, the digital devices and sensoring databanks come ahead with the exact algorithms to help the farmers and agricultural professionals to make the most appropriate decision about the exact calculation of the volume and time of the harvesting, fertilizing, irrigating, weed management, producing and selling of the products. Technology-based information and data flow related to agricultural production, which confirms the farmers for the real-time decision-making, is called the Decision Support System. In the phase of agriculture 4.0, it is inevitable to use DSS in the whole agricultural process. In recent years, Farm Management Information Systems, FMIS, have evolved from simple record-keeping into sophisticated and complex systems to support all aspects of production management. The novel decision support system for agriculture and farming is called Agro-DSS, or ADSS. DSS in agriculture is important as it provides a suite of solutions that spans the farm-to-fork ecosystem, and it is able to analyze any factors which have potential effects on crops. Farmers can obtain crop pictures by deploying unmanned aerial vehicles UAVs. Then, these pictures are uploaded to IBM Cloud for further analyses based on computer vision algorithms. The analytic results keep farmers updated with health conditions of crops. Thus, the working efficiency and accuracy of detecting crop diseases are greatly improved. On the other hand, owners of large-scale farms can use Watson or Prospera decision platform to estimate the price trending in trading markets. Under this circumstance, the time for irrigation, pollination, phenology, fertilization, harvesting, and selling can be precisely controlled in order to achieve the maximum profits. It is worth noting that the inputs to decision platforms concerns various sources, such as weather data, provided by the weather company, soil data, moisture at multiple depths, nutrient content, fertility and type, equipment data, gathered from sensors and devices, workflow data, planting and harvesting dates, fertilizer and pesticide application rates and harvest outputs, and high-definition visual imagery, collected by satellites, drones, and fixed-wing aircraft. Thus, DSS in agriculture plays a significant role in increasing productivity, allocating resources reasonably, adapting to climate change, and avoiding food waste. Components of DSS: data, models, user interface. The DSS is intended for integration into the existing farm management information systems and provides a cloud-based decision support toolbox, allowing farmers to upload their own data, utilize several data analysis methods, and retrieve their outputs. The implemented tools include predictive modeling with explanation, accuracy evaluation, time series clustering and decomposition, and structural change detection. They can help users make predictions for simulated scenarios and better understand the dependencies, interactions within their domain. DSS functions based on the following data-driven steps. First, problem understanding. In Agro-DSS, this phase is a precondition for step 1. Users, farmers, should know what their farming problem is. Second, data understanding. In order to utilize the Agro-DSS web user interface, the user, farmer, should possess a reasonable amount of domain and technical knowledge. He should be able to define the decision problem, e.g., how to improve cattle feeding in order to increase milk production, identify relevant collected data, e.g., feed composition, daily milk production, format, and upload the data and review the results. Third, data preparation. While the data preparation step is mandatory and time-consuming for the demonstrational Agro-DSS web interface users, this will be different in practice. The data will be collected and pre-processed in FMIS, and after selecting the required analysis, the data preparation phase will commence automatically, followed by communication using the Agro-DSS API services. 4. Modeling. It covers the creation of various data mining models. The phase starts with the selection of data mining methods, proceeds with the creation, training of data mining models, and finishes with the assessment of the models. Fifth, evaluation. It evaluates the data mining models created in the modeling phase. The aim of the model evaluation is to confirm that the models are of high enough quality to achieve the business objectives. Sixth, deployment. It comprises activities to organize knowledge gained through data mining models and present it in a way users can use it within their decision-making workflow. DSS models. There are a number of DSS models, which are described below. Probabilistic and optimization models. Thomopoulos et al. 2015 proposed the argumentation-based decision support system for agri-food chains that aims to optimize the nutritional, sensorial, practical, and hygienic value of the food quality. Supervised learning models. It is worth mentioning that the well-known data mining software Weka started as a project, funded from 1993 by the New Zealand government, aimed to create a data mining workbench for contributing also to the agricultural industries. Weka today features an abundance of supervised learning algorithms used by a wide research community. Bayesian models. Wang et al. 2012 developed a Bayesian hierarchical model that naturally combines information from multiple monthly surveys measured on different temporal supports, including field measurement surveys and 2 farmer interview surveys. Their results indicate that the hierarchical model produces superior forecasts to both the panel of experts and the composite estimator of the mean of a normal distribution, while providing an accurate measure of uncertainty. Other classification models. Waheed et al. 2006 investigates the potential of hyperspectral remote sensing data for providing better crop management information for use in precision farming. In the study, the ability of the classification and regression trees, CART, decision tree algorithm were examined to classify hyperspectral data of experimental corn plots into categories of water stress, presence of weeds, and nitrogen application rates. User interface. DSS produces support alerts on the basis of model output. The decision itself is the responsibility of the user. DSS is not designed to replace the decision maker, but to help in making choices by providing additional information. A decision results in an action to be executed within the crop environment. After the action is carried out, the environment is again monitored to begin a new cycle of information flow. Thus, information flows to and from the environment in an endless loop that begins with sensing and ends with action. DSS for farm management. 1. Crop planning and resource allocation. The introduction of DSS in agriculture targets to optimize farmers' decision-making process by integrating many forms of information and data which are valuable in the crop cultivation process. Moreover, the need for a substantial shift of modern agriculture attributes to more sustainable and ecologically based principles can be achieved by the introduction of DSSs in modern agriculture. Various types of data are collected and analyzed to create crop planning strategies which are less harmful to the environment and more profitable as compared to the corresponding strategies included in conventional agriculture. For example, the suggested application rates for pesticides, herbicides, or fertilizers from a DSS can be significantly lower. In addition, a DSS can forecast future disease outbreaks in croplands, rank lists for pest or weed control treatments, and maybe suggest the integration of both chemical and non-chemical-based practices in favor of crop development and productivity. However, the success of a DSS is determined by multiple factors. First of all, the cooperative efforts of a team of experts, along with technical, technological, and financial resources are required, whereas every DSS development process should be directly related to the realistic demands of the farmers. Furthermore, expert knowledge, management models, timely and accurate data, capture along with continuous feedback from the farmer after every growing season pose as key factors affecting DSS's effectiveness. Second, risk management and scenario analysis. DSS in agriculture includes the collection of data from the environment where the crop is grown. Such data might refer to climatic conditions, crop growth parameters, or the presence of pests and weed flora composition and density. Then the incorporated models in the DSS analyze the data and rank a list of suitable treatments for each case. DSS models can include rules, tips, and schedules of management, mathematical equations, and combinations of decision aids. Weeds are considered as the most important threat to agricultural production since they affect the crop production indirectly by competing with the crop for natural resources, sheltering crop pests, reducing crop yields and quality, and subsequently increasing the cost of processing. There is evidence indicating that weed infestations are the reason for a 5 to 25% loss in agricultural production in most countries. DSS methodologies might be a useful tool in terms of developing more efficient and ecologically friendly risk management strategies in modern-days agriculture. 3 DSS tools and software in agriculture. Various DSSs have been developed to help farmers take the appropriate decisions for optimum risk management in their fields, e.g., GESTINF, CPO, RIM, WEEDSOFT, WEEDMANAGER, and INFLOWEB. Moreover, Watson Decision Platform for Agriculture and Prospera, a Valley brand, are a few to name. This brings us to the end of part 1 of this module. Stay tuned for the other part.